All right, to make sure we're all on the same page, let's make sure we can do a couple of things. We want to find the inverse function for f of x equals 4x plus 8. And we're going to graph y equals x squared with this domain. So here, we're going to start by rewriting it as y equals 4x plus 8. It makes it a little bit easier to work with than this function notation. To find the inverse, we are going to go ahead and switch x and y. That immediately makes it the inverse function because we've switched the inputs with the outputs. So x equals 4y plus 8. Now we're going to solve for y to get y by itself. So subtract 8, and we get 4y equals, I'm going to switch y to the left side. It's not necessary, but I'm going to. And then we're going to divide by 4. So divide by 4. We need to make sure to divide the whole side by 4. So y is going to equal x divided by 4 is 1/4 x, and negative 8 divided by 4 is negative 2. And so this is the best form to leave our answer. Although if we really wanted to leave it like this, we could. This is the slope-intercept form. So that's usually how we would like to leave it. So this is the inverse function. Because it started in function notation, we should rewrite at the end f inverse of x equals 1/4 x minus 2. This next one asks us to graph y equals x squared with a domain. So these are all the x values we want of negative 2. So when x is negative 2, y equals negative 2 squared. And negative 2 times negative 2 is 4. Negative 1 times negative 1 is, so this is 4. So when x is negative 2, y is 4. That's where this point is coming from. When x is negative 1, negative 1 squared is positive 1. When x is 0, y is 0. When x is 1, 1 squared is 1. And when x is 2, 2 squared is 4. And because this is the domain and it's not a continuous domain, we would not connect it. All right, today we are going to be dealing with more inverse functions. We're going to find 2 new functions that we did not learn about in Algebra 1, most likely, unless you had a kind of advanced class. And we're going to be talking about a new thing called domain restrictions, and we're going to be able to solve with some new inverse operations. So we're going to do quite a bit today. We're going to start with f of x equals x squared, and here we made in our warm-up a table. So f of negative 2 was 4, f of negative 1 was 1, 0, 1, and 4. And this graph is, we graphed it, but now we actually have an entire function, and so we can connect it if we want. I'm not going to connect it just yet. But this function actually has a continuous domain. Just because I made this table doesn't mean the in-between values don't exist, and so I could connect this here. We're going to find the inverse, and so let's remember that to find the inverse of a table, we just switch the x's and the y's, and so the inverse function is 4, negative 2, 1, negative 1, 0, 0, 1, 1, and 4, 2. I did that by switching all the y values became the new x values, and all the x values became the new y values. And one thing we should notice here is that this, because the x values repeat, here we've got 4 and 4, and 1 and 1, and those x values have different y values that come out. This is not a function. And we'll see that when we graph it. I'm going to graph it in red in just a second. But before we do that, let's find the inverse equation. So we've talked about how to switch this to y equals x squared. To find the inverse, we switch x and y. So it becomes x equals y squared. And our last step here is to solve for y. Now, the inverse operation of squaring something is to do the square root on both sides. And so squaring and square root will cancel out their inverse operations, and we get y equals the square root of x. That's what f inverse of x is going to be. It's going to be the square root of x. So we can see that the square root of 4 is 2, the square root of 1 is 1, the square root of 0 is 0. Square root just asks what number times itself will give you the number inside of the square root. So what number times itself gives you 4? 2. What number times itself gives you 1? 1. What number times itself gives you 0? 0. But there's another answer to what number times itself gives you 4. -2. When we write the function f of x equals square root of x, we're only, to make it a function, we only want one answer to come out. And so we use the positive values that times themselves give you it. It's called the principal root. And we don't use this. In fact, because we don't use this in the square root function, we're going to need to do something in the original function to actually make them inverses of each other. But let's go ahead and put these points on, and we'll scratch them out in a second. We had 0, 0, 1, 1, 4, 2. We also had 1, -1, and 4, -2. And we can see that this is not a function because for each x value, there's more than one y value that comes out. And so we said we would get rid of this portion of the graph. Okay. Hopefully we can see that these are reflected from each other across the line y equals x. Ooh, I did not do a very good job of drawing the line y equals x. That should be more like this. We can see that, you know, here's this point and this point, this point and this point, this point and this point, and they're reflected across the graph y equals x, as all inverses are. And so we're going to do something a little bit weird. This function f of x, f inverse of x equals square root of x, is only defined for the positive y values because otherwise it wouldn't be a function. So the idea is that if we had these negative y values here and we had 2 y values for each x, it wouldn't be a function. And so the square root function is only the positive y values of this inverse. To make it actually be an inverse with the quadratic y equals square root of x, if we want it to be inverses with y equals x squared, we actually have to cut off part of the quadratic function. And we do this with what's called a domain restriction. So here is this part. The part that got reflected across the x-axis is, or sorry, not the x-axis, the part of the quadratic function that is reflected across the line y equals x from the square root function is just the first quadrant portion. And we can get this by saying that the equation is y equals x squared, but with a domain restriction. We say that we only want y equals x squared. We put a comma here. This means when y equals x squared, when x is greater than or equal to 0. Or we could use the domain written interval notation 0 to infinity with a bracket because it could equal 0. So that kind of gets rid of this part here. It's saying, hey, we're going to take y equals x squared, but only with a domain of x is greater than or equal to 0. And so we end up with this function. The issue that we had here, the reason that the inverse was not a function is because the y values of the original function were repeating. That way, when we switched the x and y values, the x values were repeating. This original y equals x squared, or f of x equals x squared, is a function because for each x we get exactly one y out, but the y values are repeating. And it's what's called, it's not a 1-to-1 function. And what that means is if something is not a 1-to-1 function, the y values repeat. It is a function, but it's not a 1-to-1 function because for each y, there isn't only one x. The y value of 4 has 2 different x's that go with it. This y value of 4 occurs in 2 different places. And to see if something is a 1-to-1 function, if it's already a function, you can do what's called the horizontal line test, where you draw a line horizontally. And if there are any y values that get repeated, it will not be a 1-to-1 function. If something is not a 1-to-1 function, then the inverse will not be a function unless we use a domain restriction on the original function. And the idea here is that if the y values repeat in the original function, it's not a one-to-one function, when you do the inverse, the x's will now repeat and it will not be a function. So let's think about some of the functions we've done so far. We've had linear functions. Linear functions are one-to-one functions because none of the y values repeat. When you do the inverse will be a function. So linear functions have an easy inverse. Let's think about exponential functions. Exponential functions do not have any y values that repeat. If you draw a horizontal line, it hits it each one time. And so the inverse ends up being a function. Absolute value functions are not one-to-one. And so when we do the inverse function, what ends up happening is the inverse is not a function unless we restrict the domain of the absolute value function. And so generally when you end up with a function that has a repeating domain, we find the place where the y values start repeating and restrict from there. So this absolute value function, I could have a domain restriction of x is greater than or equal to 0, and now it would be a one-to-one function. Alternatively, for a quadratic or an exponential function where it's not a one-to-one function, I could also use x is less than or equal to 0, and that would be this part, and this would also be a one-to-one function. We're usually going to restrict the domain at the vertex. So, for instance, if we have this quadratic function with a vertex at 2, 1, we can see that it's not a one-to-one function. If we want to restrict the domain so that it is a one-to-one function, we would choose a domain of x is greater than or equal to 2, because that says that all the x's need to be to the right of 2, and that would be this portion of the graph. We could alternatively say x is less than or equal to 2, and that would be all the points to the left of this. We can over-restrict the domain by saying something like x is greater than or equal to 4, and that'll be like this part. We cut off more than we needed to. We cut off some part where we could have had an additional part where there are no y's repeating, but this is still a one-to-one function. On the other hand, if I said x is less than 4, that would be, all of this still, and so you'd still have y values repeating, and this would not be a one-to-one function. So all three of these make it a one-to-one function. And sometimes we write it one-to-one as like 1-1, 1, 2, 1. But this one is not a one-to-one function. And again, the reason is because, if this was our graph, if we choose all the x's that are less than 4, well, that's this whole part, and so there are y values that are still repeating. Okay, so that's restricting domains, and we're going to look at one more type of function. Recall we learned a little bit about the cubic parent function. We want to be able to fill in this table f of -2 when x is -2. -2 times -2 times -2 is -8. A negative times a negative is a positive, times another negative gives you a negative. -1 times -1 times -1 is -1. 0 cubed is 0, 1 times 1 times 1 is 1, 2 times 2 times 2 is 8. And the graph we got earlier in the year is that we've got this point at 0, 0, a point at 1, 1, a point at 2, 8, a point at -1, -1, -2, -8, And let's recall that it has kind of this weird point where it changes from being concave down to concave up. This is called the inflection point at 0, 0. The question is this a one-to-one function? And the answer is yes, it is a one-to-one function. No y values repeat anywhere. And so the inverse will be a function. Let's see that here. When we switch the x and the y values, we'll get -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. Notice that 3 of the points are the same in both the inverse and the original function because they have the same x and y values. Remember, if the x and the y value are the same, when you switch it, it'll still be in those same points. So 0, 0, 1, 1, and -1, 1 all are the same as the points on these 3 points are the same as the 3 points on the original one, but what's different is this -8, -2. So -8, -2, and 8, 2. And this is our new function. It also has an inflection point here where the function had been concave up and is now concave down. So the function was bending up. I would have to like bend my pen up, and then and this part it begins bending down, even though it's increasing in both parts. So it's increasing, but changes concavity. Let's look at what equation we would need to do here. So this is y equals x cubed, and if I want to find the inverse, I would just switch x and y. So x equals y cubed. So I switched x and y. And similar to how the square root was the inverse of squaring something, the inverse function, you may or may not know this, the inverse function for cubing something is called a cube root. And we write that by putting a root with a little 3 inside of it. A root with a little 3 inside of it. This means the cube root. And what it's asking is, what times itself 3 times gives you the thing inside? So what times what times what gives you y cubed? And the answer is y. Y times y times y gives you y cubed. And so that's why the cube root and the cube cancel out. And of course, here we've got the cube root of x. So the inverse function is the cube root of x. So cubing something and cube rooting something are inverses. And the cube root is asking what times what times what gives you that number. What times what times what gives you 8? The answer is 2. 2 times 2 times 2 gives you 8. What times what times what gives you -8? -2 times -2 times -2 gives you -8. 1 times 1 times 1 gives you 1. And so it's the inverse of cubing. And so this is what the cube root function looks like. Again, make sure you're not writing the 3 on the outside. This means 3 times the square root of x. So this is 3 times square root of x. This means the cube root. So these are not the same. The little 3 needs to go inside the check mark to make it a cube root. Okay, so that's a new function. We've got square root functions and cube root functions. And we're going to go ahead and practice finding inverse functions. I'll walk you through this a little bit here. Here are 3 examples we're going to do. F of x equals x squared plus 5. We want to find the inverse. So I'm going to go ahead, and I know this is y equals x squared, so I'm going to go ahead and just skip a step, and I'm not going to write y equals x squared plus 5. I'm just going to go ahead and change this y to an x. X equals y squared plus 5. And I need to solve for y. So I'm undoing in the opposite order of what's happening. Y is getting squared and then adding 5. So the first thing I undo is subtracting 5. So x minus 5 is x minus 5. And if you haven't used this inverse operation before, let me make sure it's clear how it works. When you do the square root, you need to do the square root of both sides. You couldn't do the square root of either one of these things. It has to be the square root of the entire side. And so squaring and square root cancel out. But square root of x minus 5 is just left as square root of x minus 5. This cannot be simplified, nor can it be broken apart. This does not equal square root of x minus square root of 5. That's not true. So this is equal to y. And so we can rewrite this as, I'll rewrite it down here, f inverse of x equals square root of x minus 5. So the inverse function was square root of x minus 5. So the question is, do we need a domain restriction? And the answer is yes. This was not a one-to-one function, and so we needed to restrict the domain. So we do need to know that this is a quadratic. We still need to know our parent functions and to be able to recognize that if you have an x squared, it's quadratic, and so it will make a parabola. We should know from algebra 1 that x squared plus 5 has a vertex at 0, 5, got shifted up by 5, and makes a parabola from there. So the question is, what is the domain restriction that is needed? And there are two best domain restrictions. One domain restriction is x is greater than or equal to 0, because if x is to the right of 0, that is this portion of the graph. The other is x is less than or equal to 0. So what we want is we want x squared plus 5 when x is greater than or equal to 0, or we could use x squared plus 5 when x is less than or equal to 0. But to actually be the inverse that has the square root graph, the square root is always going to take the positive side of the quadratic. So in general, we'll use x is greater than, not x is less than, because it'll match up with the square root and actually make it be the inverse function. For those of you who are interested, the two graphs end up looking like this. And you can see that they are reflected across the line y equals x. This is square root of x minus 5, and this is x squared plus 5 with a domain restriction of x is greater than or equal to 0. Okay, great. So here's this next one. We've got g of x equals cube root of x minus 2. Notice that this is different than cube root of x minus 2. The whole thing is being cubed, and so the order of operations, because this is inside of a cube root, the first thing that happens is x gets subtracted by 2, and then we take the cube root of that answer. So I'm going to go ahead and switch x and y. So this is my y, and it becomes x. This is my x, and it becomes y. And I need to solve for y. To undo the last thing that's happening in this is the whole side is being cube rooted. And so I need to cube both sides. Cubing and cube root are inverses of each other. So cube root and cube will cancel out. X cubed cannot be simplified. And the last thing that's happening to y is being subtracted by 2. And so we're going to add 2. And so we get y equals x cubed plus 2. X cubed plus 2 cannot be simplified. And this was g of x. And so I'm going to rewrite this as g inverse of x. This is the inverse function to g of x. And so the question is, does this need a domain restriction? And hopefully we know well enough now what a cube root function looks like. A cube root function had this shape here, and a cube root function is one-to-one. There are no repeating x values or y values, and so we do not need to restrict the domain, so no domain restriction. This goes back to being able to identify parent functions, and when we see a cube root of something, we're like, oh, that's a cube root parent function. We know what that looks like. We know it will not need a domain restriction. Let's go ahead and answer the domain restriction for this last one ahead of time. What type of function is this? And the answer is, even though it looks a little bit weird, this is a linear function. It's a linear function because there is no exponent on x, there's no squaring, square roots, and we could rewrite it in slope-intercept form if we wanted. This is 4/7 x minus 3/7. And so we know that linear functions will make a straight line and will not be, will be one-to-one, and so we will not need a domain restriction. So no domain restriction needed here. Let's go ahead and solve for the inverse. So this is already in y equals x, so I'm going to switch x and y. X equals 4y minus 3 divided by 7. And to solve for y is getting multiplied by 4 first. That answer is getting subtracted by 3, and then that whole answer is getting divided by 7. So the last thing that's happening here is dividing by 7, and so we will multiply by 7 to cancel out the last thing that's happening. The order very much matters. We can add 3 to both sides and get 7x plus 3 equals 4y. And the last thing is to divide by 4. So we get, we can either leave it like this. It's okay to leave it as 7x plus 3 divided by 4 because nothing divides well. But if we wanted to put it in slope-intercept form, we could put 7/4 x plus 3/4, and that's equal to y. And this is a fine way to leave it. Let's talk about, I've noticed over the years that some kids struggle with graphing functions like y equals 4/7 x minus 3/7. So let's look at how that looks. So if we have a, oh man, this is ugly. Let me make a better graph. Okay, so we're going to start by graphing. So we're graphing y equals 4/7 x minus 3/7. And some Algebra 1 classes do a great job of learning how to do stuff like this, and some don't get there. The y-intercept is going to be 0, -3/7. So -3/7 is closer to 0 than -1, because -7/7 would be -1, so that would be here. So -3/7 is right here. From there, we can use the slope. The slope is 4/7 x. The slope is 4/7, which means that for every 4 you go up, we will go over by 7. So I'm going to go ahead and just graph it from there. I have to be a little careful. Going up by 4 will get me, notice every time I go up by 1, I should still be at the same place I was underneath. So 1, 2, 3, 4. This is up by 4 and over by 1, 2, 3, 4, 5, 6, 7. And that point is going to be right here. 1, 2, 3, 4, 5, 6, 7. And notice it is not at exactly 4, right? Because this was a little under 0, 4 up from there is going to be over here. Same with if I go down. I'll go down, I guess I should make this 7 here. So if I go down 1, 2, 3, 4, I won't be on exactly this point yet, right? So down by 4, left by 7, and this is my straight line. So this is my graph of y equals 4/7 x minus 3/7. Okay. There's actually a